Oh, it's time. All right. Today I am going to start the new chapter on generalized Newtonian fluids. But first, let me finish up the summary of the chapter on experimental methods, experimental behavior. So this is the handout that I've been collecting, and I'm going to give you a copy of it. It looks like it's going to be 8 pages long. So these are the experimental behaviors that I'd like you to remember. First was in almost everything's in shear, 7 pages of shear and 1 page of elongation. In steady shear flow, we have this kind of a curve on a log-log graph that you have viscosity versus shear rate or first normal stress difference versus shear rate. And I want you to really note very carefully what we're plotting against what, because there were some misunderstandings of that sort on the homework. So this is the effect at steady state. So there's no time dependence in this viscosity function. And so all that matters is what rate do you do the shearing. And you see this plateauing effect. That's the main effect. Then we said, looking at that same material function, how does it vary with a bunch of material parameters, for instance, molecular weight, and we talked about the effect of molecular weight. We talked about the effect of molecular weight distribution. And then we talked about another change to the material parameters, whether it was branched or not. Then whether or not we added filler. And all these are plots of viscosity versus shear rate, and I always plot them on a log-log graph. And then we switched from steady shear flow to small amplitude oscillatory shear. And this is a more complicated curve, and I asked you to note 3 regions of G prime, G double prime versus frequency. Again, it's a log-log graph. And you have some versions of this in the Ferry handouts as well. There's the terminal zone where the slopes are 2 and 1, the rubbery zone where G prime is flat, and the glassy zone where G prime is flat again. Then we just qualitatively discussed the effect of temperature, and then we moved on to nonlinear rheological behavior. So once we're not talking about steady shear flow, time starts to appear. So just because we now are seeing things that are a function of time doesn't mean they're not also a function of shear rate. So it becomes a function of 2 variables, time and shear rate. So we saw that in, let's say, the startup or cessation experiments, there is a variation with time, but also a variation with shear rate. So each separate curve is a startup at different shear rates. And these are again plotted on log-log graphs. This is the stress growth function and the cessation function. And again, at different shear rates, they give different functions of time. When we leave the linear zone, we also see that it's a function of strain. So this one is not a function of strain rate, but is a function of strain. This is the large amplitude step strain. And so here, and there's a typo here, this is log also. Here on a log-log graph, we see the relaxation modulus versus time, and then it's a function of 2 variables at various strains. And I showed you an example of that. Then I said, well, sometimes this multivariable function can be separated into a function only of time and a function only of strain. And that's helpful to us because it simplifies the way we think about these functions. This was not possible back here for these functions of time and shear rate. We couldn't think of some way to maybe shift them or ratio them so that they would collapse to a single curve. Their shapes actually change with shear rate. But in the large amplitude step strain, the shapes don't change. They just sort of shift downward, and so you can get a master curve, although you'll remember there were some discrepancies at short times, which we'll be able to explain with constitutive modeling, actually. And then how much you shifted it became this thing called the damping function, which looks suspiciously like viscosity, but it really doesn't have that meaning at all. The damping function is how much nonlinear effect you see as a function of strain. And you see no nonlinear effect at small strain, and then you see a nonlinear effect that increases with increasing strain. And this is predictable with advanced constitutive equations also. So going back to these slides, we finished the small amplitude oscillatory shear and the step strain. And then at the end of class, I rushed through elongation. So let's rush through those again. So elongation, which is the last topic I want to summarize, again, we'll talk about the steady case. So this is the elongational viscosity, and it's as a function of whatever's listed here. So this is actually as a function of the magnitude of the stress. Qualitatively, it's similar to the magnitude of the strain rate, which is the elongation rate. And so as a function of elongation rate, we see for at least these polystyrenes, somehow the experiments were able to come to steady state, and you see what I would call a Newtonian response for some of the polystyrenes. And then the non-Newtonian response is that there's a little thickening and a little thinning. So we saw that in a Newtonian fluid, the shear viscosity multiplied by 3 was equal to the elongational viscosity. And that's turning out to be the case for these polystyrenes. And so very often these are plotted as the Troughton ratio, the ratio of the elongational viscosity to the zero shear viscosity. Now, this is the case when you're able to get to steady state, but here are some data that show that a lot of elongational measurements don't come to steady state. So I notice here also that there's missing labeling. This is time, except it's not going to let me write t here. This is time and this is time. Okay. So as a function of log stress growth versus log time, you can see that they don't come to steady state except at these very low rates. At these low rates, they come to steady state. And that's in the regime where this is measured. Okay? So outside of that regime, you see that as you start the experiment and you're hoping it's coming to a steady state, it just maybe takes off. What it takes off to depends on the elongation rate. So these are at increasing elongation rate this way. So here are more data. This one is polypropylene at the top, and this is linear low-density polyethylene at the bottom, and they both show this tendency to follow a lower curve for a while for some low rates, but that at higher rates they take off. So the part about this that I'd like you to remember is that elongational viscosity at low rates is usually equal to 3 times the low rate shear viscosity. And that's Troughton's law. And that's what we were seeing here. So at sufficiently low rates where nothing too exotic is happening and you are able to get to steady state, the plateau that it plateaus out to is equal to 3 times the elongation, the shear viscosity. We don't actually define a eta bar naught. We could, and maybe we should, but we don't, so I won't introduce that. That'll be too confusing if I make up nomenclature nobody else uses. But instead, people will write this, 3 times eta naught for the zero shear rate. And then the other thing to remember is that at high rates, eta bar plus, which is the growth coefficient, does not come to steady state. And that's this strain hardening effect on this slide. We don't need to know that terminology, but this is the effect we're looking for. So eta bar plus on a log-log graph looks like a regular startup curve of steady shear viscosity. It plateaus at 3 times the shear value because that's the low rate effect. And then at higher rates, it does this. It just takes off. This is increasing epsilon dot. And that's the last that I'm asking you to know. So I'll put these on the web, and I'll bring you a copy next time as well. Now there's just one more slide of data I'll show you. This is step strain data done in the biaxial extension mode. So these are two plates, and the sample starts as a tall sample, and then you suddenly squish it. And if you lubricate these plates, it'll just slide into its new position, and it's a biaxial extension. And you can measure a step strain modulus in this flow, and it matches 3 times the shear value it matches the shear value at low strains, and also strain thins the same way that the step strain data do. And this is a biaxial damping function as a function of strain. And so again, you see that it's kind of a plateau at no change, no strain dependence, and then it comes down. And then these are some various model fits from the paper that I took it from. This is on low-density polyethylene. So there are some experiments other than the steady elongation or the startup that we can do. These are more esoteric, though. These are more unusual. These data happen to be taken in the laboratory when I was in graduate school. It's useful to have this elongational function, and again, when we're looking at this elongational damping function, when we're looking at complex constitutive equations, but unfortunately not too many people are able to do this measurement. So elongation, it's difficult to perform, it's difficult to obtain steady state, and it's important. So this is an explanation for why there are many laboratories that are still going to great extents, very difficult experiments to try to measure these, but they are relatively unusual, as are the unsteady experiments. So that's the summary of the data that we're going to be trying now to somehow find a constitutive equation to describe. So we've got a lot of background, and we finally reached the point where we're ready to model it. So this is our new chapter. I forget which one it is. But we're now going to start constitutive modeling. So the bottom line is that we have non-Newtonian fluids. So that means on these materials we take data. And our goal is to determine the constitutive equation. Now, this is, maybe by now you agree with me that this seems like a very difficult task. This constitutive equation is a tensor equation, and it predicts what the material will do in any flow. And as we saw from the last 2 chapters, we're only able to tell what the fluids do in very defined flows. We have to pick a flow, then we have to pick exactly how to put that flow on. So we can pick shear. Do we do it steady? Do we do it oscillatory? Do we do it startup? Do we do it cessation? All the different things we pick give us different things. So now we're faced with the task of having to guess what this equation has to be in order to get the data that we've seen. And it's a big task. It's a very big task. So we're going to approach this step by step by trying to just begin with things we know. For instance, we know a lot about Newtonian fluids. And then incrementally improve our model so that we can mimic the kinds of behaviors that we saw of the various non-Newtonian effects. So we're going to start with page 1 of our experimental data. We're going to start with trying to mimic this steady shear effect and the fact that there's a first normal stress coefficient. So we're going to try to mimic this shear thinning effect. And we're going to have some success with eta, and we're going to have no success at all with psi 1. then that will bring us through this next chapter on generalized Newtonian fluids. In the next chapter, actually, the other thing that we'll get in this generalized Newtonian fluid chapter is we're going to get some amount of success at predicting these startup effects and cessation effects. Not perfect, but some. Okay, we're going to get some success there. Then we're going to try to handle some of these other effects like this 2 and 1. We're going to be able to predict that in the chapter on generalized linear viscoelastic fluids. And we're going to be able to understand at least the small strain version of the large amplitude, of the step strain experiment. Not the large amplitude part, but at least this low strain part. So we're just going to pick off these observations we've got and try to make them, find out what in the math would cause those things to happen. What characteristics of this equation would allow us to capture those various material behaviors. Okay, so the first one, we've actually almost derived already, the generalized Newtonian fluid, but now let's do it the right way. Okay, so we're looking for constitutive equations, and we're starting with the one constitutive equation. We know the Newtonian. The Newtonian constitutive equation is that the stress is proportional to the rate of deformation tensor del V plus del V transpose. Now we know that this is wrong, so we say that in general what we're looking for is some function of gamma dot that will be nonlinear and will be a function of time, so that we can get time effects, memory effects, and nonlinearities. As I said, we're going to start with the first observation, which is the observation of shear thinning, which is replotted here on a log-log scale. We have the zero shear viscosity as a function of shear rate. And we're going to first design a constitutive equation that shear thins. So to do that, and as I said, we've almost done this already with our little fake constitutive equation. Let's first write the Newtonian equation in tensor form. So here in shear flow, because remember, as always with our material functions, this is a material function, it has kinematics that go with it. These are the kinematics. It's a unidirectional shear flow. So when we put that and make del V transpose out of it, we get this tensor. So the Newtonian case says multiply that by minus mu, and you get the stress at every position and every time for this flow. And from that, we calculated the viscosity. Now, if we don't have a Newtonian fluid, we can generate the same sort of thing in shear flow. And what we noticed previously was that the viscosity out front here is the viscosity, this parameter out front of the model, which we then turned into the viscosity, is the parameter that gives the steady viscosity value in a Newtonian fluid. So if we put this function in front instead of this constant, then we should predict this behavior. So we're going to just replace this constant with a function, arbitrary function so far, and see how far that gets us. Now, this is shear flow. So shear flow has this velocity. Gamma dot is the same for all shear flows, no matter what we pick for the constitutive equation. Then we put this function out front, and we've got a prediction. But the thing is that we're making this prediction and this adaptation in shear flow, but the implications go far beyond shear flow. Okay? If I say that the stress is going to be this viscosity function times the rate of deformation tensor in shear, then I'm also saying that the stress is going to be that function times the rate of deformation tensor in any flow, any arbitrary flow. Now, we haven't checked every flow. We've only checked this flow. So this is a brash assumption. It's a very brash assumption. Nevertheless, we're going to give it a go. We're going to see, we're going to make a guess that this is an interesting constitutive equation. We're going to put it through its paces by calculating various material functions, and then we'll know what the predictions are, and then we can check against our handout here whether that's really what materials do. Okay. This constitutive equation is based on the magnitude of the rate of deformation tensor, gamma dot, which is one of the invariants of the tensor. So this is the definition of the magnitude of the rate of deformation tensor. And so for any flow that we have, we can, any flow that is one of our standard flows, we can certainly calculate all these derivatives and then calculate this magnitude. Now we're using this magnitude to stop the problem that we saw in the homework and in the previous lecture, which was that the only way to make predictions for any flow is to define your constitutive equation with a parameter that you can calculate in any flow. I can't just say dv1 dx2, because what if the flow's in the 3 direction? Then this parameter doesn't make sense. But even if the flow's in the 3 direction, maybe all of these terms are 0, but I'll get something out of these terms with v3, and I'll be able to calculate a magnitude of the rate of deformation tensor. So this is our first real non-Newtonian constitutive equation. It's called the generalized Newtonian fluid. I will usually say GNF. The generalized Newtonian fluid is exactly the same as the Newtonian one, except that a function has been placed out front here. And as of yet, I haven't said what function that is. I also don't know how good this is, but it's just my guess. So that's what I'm saying in this slide. You know, how do I know this was a good idea? Okay, and the answer is I really don't. Okay, there's no real justification. It's just a guess. It's an empirical model. So this is an empiricism. We're giving it a try. All right. So after we propose such a model, we have to look at it and see how well it does. So that's what we'll do next, is check this model out and see how well it does. Now, we can see a couple of things from this flow just by looking at it. We've assumed that tau and gamma dot are proportional to each other. All right, that's one of our rash assumptions. There's also no explicit time dependence in this model, so it doesn't look like it would do a very good job of calculating things that are dependent on time. And the only nonlinearity in this function is this rate of deformation magnitude, gamma dot. So we'll see if those were good assumptions or not. Okay. So in order to check this model out, we have to actually be more specific about this eta function. So we're going to pick something that matches the data. And in fact, the first thing we're going to pick is something that's really simple so that we don't have a lot of complications here. So here's the data. The data, as you've seen before, has a 0 shear plateau and then a high shear rate thinning part. And that shear thinning part is the part that happens in the most important, industrially important shear rates. So if we just concentrate on this thinning part, we'll get our first model. We'll pick a eta as a function of gamma dot that just mimics this straight line part. So that's the power law model, which you've heard of probably. So the power law model says pick your viscosity as a function of shear rate to be a line on a log-log graph. So the slope of this line is going to be n minus 1. And the intercept means where log eta goes to 0, so that's here. Okay, the intercept is log m. So on a log-log plot, if you take the log of this function, you get the log of the viscosity equals log of m plus n minus 1 times log of gamma dot, which is in shear flow is equal to the magnitude of dv1 dx2. So this model, the power law model, as I said, gives this shear thinning behavior. It actually also captures Newtonian behavior if you let n equal to 1. But most importantly for us is that we're adding a little bit of nonlinearity to the model by putting this chosen viscosity function out front. The formal name of the power law model is the power law generalized Newtonian fluid. It's a generalized Newtonian fluid because tau is proportional to gamma dot. The particular GNF that it is the power law model or the Oswald-de Waal model. Usually for most polymers, n is between 0.5 and 1. Now, if we want to go back to the data and really capture everything, both this zero shear part and the thinning part, then we need a little bit more complex model, and that's this second power law model. This is the Karo-Yasuda model. So again, here's the generalized Newtonian fluid. And then here's a much more complicated function to put out front. So this is a complicated function. It won't look too familiar to you. Let me plot it for you. It looks like this. It comes to a constant plateau. Okay, it comes to a constant plateau. It shear thins like a power law. And if you want, you can make it approach a constant value of viscosity at high shear rates. And you can also vary this portion of the curve, this curvature. And remember, when you varied molecular weight distribution, this portion of the curve changes. So this portion of the curve we're also able to change. Right? Here's the eta naught. That's if you take the limit as gamma dot goes to 0, you get that it approaches eta naught. If you take the limit as gamma dot approaches infinity, you get that it approaches eta infinity. The A parameter determines how this curvature turns out. The lambda parameter determines where this happens, where the curve decides to start thinning, okay, is determined by lambda. And n, just like in the power law model, determines how steep is this slope. Okay, determines the slope here. If we want to capture shear thickening with a generalized Newtonian fluid, this is real shear thickening. Okay, this is real shear thickening, but we can make idealized shear thickening, at least these parts of it, by doing a power law model with a n greater than 1. This is unusual, but it might be helpful to model shear thickening under some circumstances. Now, I've got a few more models I can show you, but let me take a break and let's use this a little bit and see what the generalized Newtonian model predicts. So I think I asked you to do some of this in the homework. For instance, let's try startup of steady shear. Let's look for the power law generalized Newtonian fluid in startup of shear. And as usual, when we did these predictions with the Newtonian model, we solved them the same way. We start with the kinematics and the constitutive equation. And we put the kinematics into the constitutive equation and then calculate the material functions. Okay? So the kinematics of startup are that we have shear flow. Where the sigma dot function is 0 and then something. It's 0 for time t less than 0, and it's something for time t greater than or equal to 0. So we need to put those kinematics into this constitutive equation. Tau equals eta of gamma dot the scalar, excuse me, minus times gamma dot the tensor, del V plus del V transpose. Now I'm going to do this a little quickly. But remember that gamma dot is the same for this flow no matter what constitutive equation. So we've calculated that before. Gamma dot is equal to 0, gamma dot 0, 0, gamma dot 0, 0, the rest zeros. So that is just, this gamma dot function is just dependent on the velocity field, del V plus del V transpose. And in shear flow, startup of steady shear, this is always the velocity field. So that part, it doesn't slow us down. In startup, oh, excuse me, I put the wrong one. This is only for t greater than 0. And gamma dot is equal to 0 for t less than 0. So now we need to make the constitutive equation. And it looks a little complicated, okay? The constitutive equation is minus eta of gamma dot, where eta is equal to m gamma dot to the n minus 1. Gamma dot is the magnitude of gamma dot, the tensor. So we need to go back in our notes and find out what was the formula for that. So there it is. The magnitude of the tensor is 1/2. Actually, we've defined this a variety of ways, but it's this sum, which is also equal to gamma dot double dotted with gamma dot. All right, so gamma dot, let me go back to writing gamma dot, the tensor, with the sigma dot in it. That's what I should have done the first time. So that encompasses both below time less than 0 and time greater than 0. To calculate the magnitude of gamma dot, we have to calculate the square root of 1/2 gamma dot double dotted with gamma dot. Which is, I'm going to use my fingers now. It's 1, 1 times 1, 1, 1, 2 times 2, 1, 1, 3 times 3, 1, 2, 1 times 1, 2, 2, 2 times 2, 2, 2, 3 times 3, 2, 3, 1 times 1, 3, 3, 2 times 2, 3, and 3, 3 times 3, 3. So you just go across the diagonal and multiply across the diagonal to get the product. So what we get is 0 plus sigma dot squared plus 0 plus sigma dot squared plus 0 plus 0 plus 0 plus 0 plus 0. And so we get it's equal to the positive value of sigma dot as a function of time. So that's the only sort of new tricky thing that comes with the generalized Newtonian fluid, is that the generalized Newtonian fluid has the magnitude of the rate of deformation tensor in it, and so you need to calculate it. And we're going to see this also when we solve flow problems with the power law model. All right, so then continuing on with the calculation, we're now going to formulate the constitutive equation. Tau equals minus m gamma dot to the n minus 1 times gamma dot the tensor. That's the power law generalized Newtonian fluid. We've calculated gamma dot. We've calculated gamma dot the tensor. So we just plug them all in. It's equal to minus m. Sigma dot is always positive, so I don't need the absolute value signs. N minus 1 times the gamma dot tensor, which is 0 sigma dot 0 sigma dot 0, 0, zeros. Now we can multiply this in, and when we multiply this by this, we get just sigma dot to the n. So we get 0 minus m sigma dot to the n. Now sigma dot is this crazy function. It's 0 and then it's a constant. So we can break this into two pieces, or we can first do the definition. We can see first of all that psi 1 plus is 0 because all the normal stresses are 0, and psi 2 plus is 0, all the normal stresses are 0. And eta plus is equal to minus m sigma dot to the n over gamma dot naught. So those minuses cancel, and it's equal to m sigma dot to the n over gamma dot naught. If we plug in what sigma dot is equal to, we have to break it up. At t less than 0, that must mean eta plus is 0. And at t greater than or equal to 0, eta plus is equal to m gamma dot to the n over gamma dot naught to the n over gamma dot naught, or m gamma dot naught to the n minus 1. So this is our answer for eta plus as a function of time and shear rate. Time and shear rate. And so it's actually very similar to the fake model that we did in the homework, this response. The difference is that this constitutive equation is going to work when we do similar calculations in elongational flow, whereas our fake model had the problem of having the gamma dot naught in the model itself. If I go back one page, our model did not have any reference of shear in it until we substituted shear into the problem. When we started, there was no reference to shear here, and that makes it a legitimate constitutive equation. So if we sketch this, when time is less than 0, it's equal to 0. And when time is greater than 0, it's equal to some number. And there's no time here. This is how you have to think about these as I ask you to sketch them. They're going to get more complicated, unfortunately. Okay? There's no time here. You're sketching versus time at a fixed gamma dot. So think of it like way back in your earliest math days of algebra when you were plotting a function. You're going to know the model has m and n. Those are parameters. Somebody has to give you those. What's gamma dot? Well, gamma dot, the answer that you're getting for eta plus depends on what gamma dot you use. So you're going to pick different values of gamma dot naught. So you might pick 1, 10, and 100, something like that. And if I pick 1, 10, and 100, I can just pick some random m's. Let me pick m is equal to 10 to the third, and n is equal to a half. Then eta plus, at that value of shear rate, is going to be m, so 10 to the third, times gamma dot, which is 1, times 1 to the minus 0.5, so 10 to the third. At 100, it's going to be 10 to the third times 10 to the minus 0.5. And at 100, it's going to be 10 to the third, that's the m, times 100 to the minus 0.5. So you can plot these functions just by putting some representative values in. The bottom line is it's not dependent on time. So whatever number it steps up to that value for all times. And then as you go to higher and higher shear rates, it goes to lower and lower values. We can also see this from a sketch. If we looked at our original function, eta of gamma dot as a function of gamma dot, we know that this is a power law function which looks like this. And so when you pick off different values of eta that it steps up to, okay, this eta in our case is equal to m gamma dot to the n minus 1. The same answer we got, except evaluated at gamma dot naught. And so it's the same deal, that at an increasing shear rate, it goes to smaller values. So let me flash that up again. We started with the question, how do you make a prediction with such a model? And the answer is the same way we did with Newtonian, with a little bit of extra complication. We start with the kinematics. In order to calculate the constitutive equation from the kinematics, we need the magnitude of the rate of deformation tensor. So we calculate the magnitude of the rate of deformation tensor. Then we just plug everything in and form the constitutive equation. And there's the prediction for this flow. We've plugged in one particular flow, so this is now the prediction for this flow only. And then we use the definitions of the material functions to calculate those values. We get our answer, and then we can interpret our answer. I'm going to show you next time how to do a calculation with a generalized Newtonian fluid of a flow itself, of a velocity field, which is sort of a different concept. And we've done that with Newtonian fluids, so you'll see some parallels there. I did this example with the power law model. You can do it with the Karo-Yasuda. It only really becomes complicated after here, okay? Up to here, if I put eta in here instead of this actual, if I put a different eta in here, this is all going to be the same as before. I have to put the Karo-Yasuda eta in here, and then that just changes this final value. It's going to step up to the Karo-Yasuda value, and so this will look a little bit different. In fact, for the Karo-Yasuda, can you see what it will do? Because that function looks like this, the Karo-Yasuda model will predict this for several values of low shear rate, then it'll thin, and then it'll sort of stall at the lower value, because that's what the viscosity function does. It's at a high value for a long time, and so we'll get that it steps up to that value, and then it'll step up to these lower values, so it'll go down, but eventually at very high shear rates it'll keep stepping up to whatever this eta infinity value is. Now, the generalized Newtonian fluid can be used for instance, mayonnaise as well. It can be used for yield stress materials. And it's just a question of writing a different viscosity function. So usually when we describe a yield stress material, we plot shear stress versus shear rate. Newtonian fluids, shear stress is proportional to shear rate. And for materials with a yield stress, you have to get up to the yield stress first, and then it'll flow like a Newtonian fluid. We can write this function as a shear rate. Here's some real data of a yield stress fluid. So you see that this material is Newtonian, as is 5, but gradually a yield stress is appearing in this material. Its intercept is non-zero. This is polymethyl methacrylate in water with various zeta potentials, so various changes to the solution properties. So here's that curve. Shear stress is equal to yield stress plus a constant slope times the shear rate. We can turn that into a viscosity function by dividing through by gamma dot. So we divide through by gamma dot, and we get our final function. When we look at this final function on a log-log graph, it looks Newtonian at large shear rates, and at small shear rates, it actually approaches a slope of -1, which is what I show here. If you divide, here's my final viscosity function. If I take the limit as gamma dot goes to 0, I get that it varies with shear rate as, here's a constant, minus log gamma dot. So on a log-log graph of viscosity versus log shear rate, it would give a straight line with a slope of -1. This is therefore the viscosity function for a Bingham plastic. It says that when the stress is below the yield stress, the viscosity is infinite. Okay? When the stress is below the yield stress, it doesn't flow at all. And above the yield stress, it flows like this. So this is a 2-parameter model. It has the yield stress in it, and it has the steady shear viscosity during this portion of the curve, the viscosity when it's actually moving. This is an interesting viscosity because we had to make the discriminating factor between the two regimes the magnitude of the stress tensor instead of the magnitude of the rate tensor. So this is a little bit different, and it has some challenges when applying, but the rules are the same. Now, there are a lot of other generalized Newtonian fluid models in the literature. Okay? You've seen the power law model and the Bingham plastic. There's also, this is called the Ellis model, which is also based on the magnitude of the tensor. The 4-parameter Corot model, which is a simplification of the Corot-Yasuda. The Cross-Williamson model, which is another simplification of the Corot-Yasuda. The Dickey model, which is got some exponentials in it. The Casson model, which is very interesting, lots of square roots of stress in it, a little bit harder to apply. Herschel-Buckley model. This Herschel-Buckley model is just like the yield stress model. Okay, the yield stress model had this term, but it had just a constant viscosity here. This one's got a power law model. And the Dickey-Turcotte model. So these are all different models, but all they do is change the shape. If I go way back here, all they do is change the shape of this viscosity function. They're all fundamentally the generalized Newtonian fluid model. So we can treat them all very similarly under some circumstances because sometimes it just doesn't matter what eta is. But if eta has an interesting shape, for instance, the Casson model is used for blood, then you can use different generalized Newtonian fluid models. So if you look at the book, at the homework problems that I did not assign, there are a whole bunch of problems in the back of the text, the back of this chapter, that say, calculate startup with the Ellis model, calculate flow in a tube for the Ellis model, or for the Corot-Yasuda model, or something like that. So all of these are open to you. They do get a little bit tricky sometimes, so I don't usually ask you to do a lot of those calculations, but they all have the same features to them. All right. The idea of predicting material functions follows the same procedure that we used for Newtonian models and for this example of the generalized Newtonian fluid. What I'm going to start with next time, I think, is a calculation, another use of the constitutive model, which is to go back to something like flow in a tube of a fluid. But now this time, let's not calculate a Newtonian model, let's calculate a non-Newtonian model. And so this will be the case of doing flow problems with the generalized Newtonian fluid. And for the flow problems, we have to go back and remember what we did for the Newtonian case. We'll be answering questions like, what is the velocity profile for pressure-driven flow in a tube, for instance. We can also answer these kind of questions with the power law generalized Newtonian fluid model, and I'll show you how to do that. Okay, because after all, it's the constitutive equation. And with the constitutive equation, we can calculate flow fields and we can predict material functions. So we'll do the other half of that next time on Friday.